Welcome to this video, Fourier transformers from Fourier series and Fourier transforms of singularity functions by Gindel Someshwar Sairam Prasad. So let's go. First of all, introduction. What is Fourier series? Fourier series, we can represent a periodic signal. Signals can be represented in time domain and frequency domain. So in Fourier series, the signals are represented in periodic signal. Fourier transformers to extend with a non-periodic signal. So we can analyze the non-periodic signals by Fourier transforms. So it used in basic modern signal processing and communication signaling and physics and etc. We use this Fourier transforms and Fourier series in this. So let's recap Fourier series. So for periodic signal x of t with a period of t, x of t is equal to summation n is equal to minus infinity to infinity cn e jn omega naught t. You can see in that image where omega naught is equal to 2 pi by t fundamental frequency, where cn is a Fourier coefficient. Here cn is equal to 1 by t to t plus 1 x of t e power minus j n omega naught t dt. So you can see in that image. That's it. So what is this? From we can go to limitations of Fourier series. So work only for periodic signals. So it's can't directly help to we can find not a periodic signal or infinity during signals. So example exponential decay or rectangle pulse in not periodic. So this we can find with Fourier transforms. So Fourier series does not help with that transition of Fourier transforms. So how can we derive Fourier series uh, from Fourier transforms? So Fourier transforms. Uh, Fourier transforms is we get a frequency domain. So from we get Fourier transforms from Fourier series to analyze aperiodic signals. Extend it Fourier transformers ideal let t is equal to infinity. So where fundamental frequency omega naught is equal to 2 pi by t, where t is equal to infinity. Anything infinity by 2 pi is equal 2 pi by infinity is equal to 0. Frequency components become continuous instead of discrete. Okay, in this Fourier transformers, the frequency components are become discrete and continuous. Harmonics, continuous frequencies becomes. In Fourier series, harmonics become in Fourier transformers continuous frequency. In Fourier series, summation become integral in Fourier transformers. This is ideal about Fourier transforms. So mathematical analysis. As t tends to infinity means the time period in infinity where Cn is equal to 1 by t minus t by 2 into by limit t by 2 x of t e power jn omega naught t dt. So you can see in that image it become x of omega is equal to minus infinity to infinity over integral x of t e power j omega naught t dt. This Fourier transform of definition. So therefore Fourier transform where we can see in that f of omega is equal to integral minus infinity to infinity f of t e power j omega t dt. So from inverse we can get a Fourier series. Let's we can integrate Fourier transformers inverse, we get a Fourier series. Therefore f of t is equal to 1 by t minus infinity to infinity f of omega e power j omega t d omega. You can see that in image. Application of Fourier transforms. where we can apply this spectrum analysis, filtering, modulation, audio, image processing, LTI means linear time invariant systems, responses, etc. We can use Fourier transforms. For suppose we have a periodic signal, means the signal does not repeat over a time with in some intervals, so it's a periodic signal. So we can analyze how its frequency, how these characters by Fourier transformers. So this is all about Fourier transformers. Let's recap again. F of omega is equal to minus infinity to infinity f of t e power j omega t dt. This is we get from Fourier series. That's it. Fourier series versus Fourier transformers. So Fourier series, where Fourier series is periodic signals, Fourier transform is non-periodic signals. In discrete spectrum in Fourier series, a Fourier transform is continuous spectrum. In Fourier series summation, Fourier transform is integration. So you can see that in image Fourier series versus Fourier transformers. So we can get Fourier transforms about an idea that an integration we use, and it's a continuous spectrum and non-periodic signal. So that's it. We can derive Fourier series from Fourier transformers, that's inverse. We can get again Fourier transformers from Fourier series, that f omega. So the x of t become x of omega. So the period, the function become x of omega. So the axis, the x-axis in Fourier series time domain, the Fourier transformers is frequency domain. That's it. Fourier transform of singularity function. What is singularity function? The singularity function is the unit is one, that is basic singular means the function value is a singular one over periods interval. It is basic building blocks in all systems, used for define impulse response, this step signals, odd symmetry, anything else. So unit impulse is equal to integral minus infinity to infinity del of t dt is equal to 1. The del of t tends to 1, the shifted impulse. So we can get by Fourier transform analysis, we use that mathematical analysis. So del of t minus t naught tends to in this e power minus j omega t naught. That's it. You can see that in unit impulse function, where unit impulse is a like that impulse means you can see in that graph that signal is unit impulse means that signal x of means x of t in x of omega, that is in their Fourier transforms. We don't get in Fourier transforms image. This is all these images are Fourier transforms, examples of unit impulse function. You can get an idea what is how it's a signal and how this signal is so that's it. Unit step u of t. So definition, u of t is equal to 1 where interval t greater than or less than greater than or equal to 0. So we can get graph 1 where t greater than 0 or equal to 0. Again the u of t becomes 0 when t less than 0. So you can see that in image u of t, that function is over period 0, that become x of t is in frequency domain, it that give. So in that image you can see that x of omega, that become this x of t over 0 to 1. So that's it. So signum function. Let's go to signum function. What is signum function? Again, it represent with sgn of t. We can use that where plus 1 t greater than 0, minus 1 t less than 0. So s of omega means the signum function Fourier transform is 2 pi j omega. You can see that in image. Here you see Fourier transform function of that image and Fourier series of that signum function. Relationship between functions. What is that relation? So if you know that relation, we can get any function from one function. So d by dt of u of t is equal to del of t. So we can differentiate u of t, we can get del of t. Again del of t integration, you get u of t. That's the relation. Again in signum function, signum of t is equal to 2u of t minus 1. So from this relation we can find any signal. We have one signal, so these are relation between three signals. We can get any signal. So these three signal are basic blocks of signals and systems. These three are singularity functions. So Fourier transform summary table. You can check that function again, that in summary table del of t Fourier transform is 1. Del of t minus t naught is equal to e power j omega t naught. U of t is equal to pi of del of omega plus j 1 by j omega. Again signum of t 2 by j omega. So we can get Fourier transforms for this Fourier transform from these functions. Here the values you can remember. We can get that by doing mathematical analysis, Fourier transformers to that signal. Application of singularity functions. So applications where singularity function use impulse. We use it system responses, that it's step switching signals, signum the system and order or even we can signum the signal is symmetry or odd or even analysis we can use. So this the three signals we use in digital signal processing, communication and control systems wherever, and analysis of basic signals. So from final session we can get Fourier transforms and Fourier series we can discuss, and Fourier transform of singularity functions. So let's recap again. We can close this. Fourier transforms f of omega is equal to minus infinity to infinity f of t e power j omega t dt. That's it. Again you can check that in Fourier transform summary table the values. You can remember that for different functions, the different Fourier transform values you can remember that. So that's it. Thank you for giving this opportunity. You can ask any doubts in comment section, so I can answer, and this is all about these functions, Fourier transforms of from Fourier series and Fourier transform of singularity functions. So we end this session. Thank you for giving this opportunity. Bye bye guys. Thank you very much for watching.